Hi, good evening, and welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really just answering technical questions that have come in from during the week. So rather than chatter, I'll just get straight into it. And I want to say today's the 1st of December, but we do have a slight tendency to kind of go early on these things. So rather than doing them on the Sunday, which would be the 1st of December, tonight is the 30th of November. So forgive me for going about approximately 12 hours early, actually. Just FYI, at midnight tonight, the old discount code for the web store will expire. If and only, unfortunately, if you purchase through the Shopify web store, I have a link to it here, you can get a 10% discount in December. It's important to say that it's only through the Shopify website because otherwise it's an expense to us to process bank, etc. Anyway, that said, there's a discount for the Shopify website. I just want to say as well that a big emphasis that we're making at ZP at the moment then is on this Sense It All platform. So in fact, I do have it obviously in front of me. I'm going to do a couple of demos tonight as well. So in fact, you can see me sitting here with a bit of, it sounds a bit unusual, but I've got a bit of ginger root here. I've got all sorts of samples going on. And I will probably run some samples later on. So, but a big thing that's going on at ZP at the moment is we're really pushing, let's say, on this Sense It All platform. Why? Because we see this as one of the best ways of translating scientific research into products. And I'm going to talk about two examples this evening. One for tetracycline and one for dopamine. But anyway, I'll get to that in a bit. But if you're interested in screen-printed electrodes, or you're interested in potentiostats, and more importantly, you're interested in translating the science out of the lab and into the real world, then please watch the rest of this webinar. So questions tonight. I'm starting to support one of our clients in the use of their Sense It All platform and starting to maybe think about protocols so that their students can do lab testing. It's probably a bit of a journey for me, but I'll give you a few ideas tonight. Question number 2, POC2 measurements. So at Zimmer and Peacock, on our web store under biosensors, we have a whole host of electrochemical biosensors, and many of them represent metabolites. If you go and have a blood test, they may measure something like 100 parameters in your blood sometimes. But there's about 14 parameters that make up something called the comprehensive metabolic panel. And on there is PCO2. So I'll talk about measuring PCO2, which is the partial pressure of carbon dioxide in the blood. Some generic questions on biosensors, which I'll answer. Fabricating lactate sensors in the lab. Measuring tetracycline antibiotics in milk. And measuring dopamine. And then we'll be coming to the end. We do some more focused webinars, so I'm sorry to be a bit passionate on this, but I'm very, very interested in the translation of electrochemical biosensor development into impactful products. I think there's going to be a little bit of an issue in the next few years where governments are going to say, if this product's not translating, or you're not just demonstrating translation, let's say, into the real world of science and technology, then funding's going to start drying up. So it's something I'm kind of quite passionate about. Anyway, we'll talk about commercialization on the 7th of January 2025. I know today's only the 30th of November 2024, but got big breaks coming up, let's say. But anyway, we'll do some webinars specifically on commercialization of electrochemical biosensors on the 7th of January 2025. We will do a wearables webinar. You'll see something pop up this evening. We are going to be launching some new products in the wearable space, so please watch out for that. And we will be talking on the 10th of December about translation of academic research into impactful products. So you'll see that covered a little bit this evening as well. Just to say, if you are interested in wearable biosensors or point-of-care diagnostics, we do an in-person workshop. I've got a link to it here. Any links that pop up, by the way, I'll make sure I put them underneath the video. On wearable and point of need testing, this is a 2-day workshop in January in Norway, hosted by myself. This won't be just it just won't be one of these kind of workshops where you just listening. It's actually extremely interactive and very lab based. So hopefully that it might be interesting to you. So just FYI, it's great. People are really adopting now this Sensi-All platform, and so they should. I mean, it really is a very powerful little technology, and it's quite nice because the early people who first started getting it, it comes in a kind of potentiostat mode, and it also comes as a sort of, it's also something that we ship into the food industry for testing in food. And I'm really pleased, we've got this chili and ginger assay on it, got a caffeine assay coming on it as well. It's a really powerful little technology. Anyway, the reason I'm just starting to think through a question that somebody's asked me, which is, how to use it in the teaching in labs. I think one of the easiest things to teach in labs is actually cyclovoltammetry. There's a whole bunch of literature on cyclovoltammetry. Cyclovoltammetry is not a bad place to sort of start. And in fact, when you turn on the potentiostat, it kind of starts in this kind of mode. So I was thinking about doing, the first thing that maybe a lab practical could be is the cyclovoltammetry of ferricyanide. Because why do I say that? Because ferricyanide is kind of, it's a very easy redox system. You really can't go wrong with it. If you make up a 5 millimolar solution of ferricyanide in something like 1 molar potassium chloride, then you've got a very standard stable solution, and it's easy to do cyclovoltammetry on it. I'm going to bring in some of my kind of philosophies in this evening. So I did do that test, and in fact I did it on one of these hypervalue carbon electrodes. I absolutely love the fact that it wasn't by design, but we started putting them into this cartridge format, and it just makes such a difference. Both, in the teaching perspective, but also in the imagination of, how can we turn electrochemistry into a product? Let me just kind of slightly go off on a tangent here and just sort of snap this down and say, hey, this is a screen printed electrode. People are quite used to screen printed electrodes. They're floppy, ugly things. But look at this thing. It's elegant. It's easy to hold. You don't have to put your fingers all over the device itself. It's really been thought through. And hey, I want to plug it into this potentiostat. Do I have to slot it in some awkward manner? No, I just click it in. So really kind of a nice, let's say, tool for, people in that sort of teaching lab situation. But let me go back to that teaching lab situation. So what's an easy first experiment to start thinking about for labs? I would say cyclovoltammetry. And in fact, I should cyclovoltammetry and then settings. And then I've got the settings up. I should just go back here actually and just sort of make the point that this is a powerful little potentiostat. So I'm just going to scan a QR code, square wave, cyclovoltammetry. So by just scanning this QR code, this is in Bluetooth connection with this. If I go continue here, I've got all my settings ahead of me, and then I can start the measurement. So it's quite straightforward to go into that cyclovoltammetry mode. Now I've put the conditions here that I used, and I did that, and I got a cyclovoltammogram for the 5 millimolar ferricyanide in the 1 millimolar potassium chloride. I actually I actually got that, as you would expect. Now, I have a really strong philosophy on, I always want to commercialize things. So, a bit of a trick question here. What's wrong with my settings here? And the answer is, there's nothing wrong with my settings here. This is kind of quite classic. I start off at minus 200 millivolts. I go to 600 millivolts. I do a scan rate of 10 millivolts per second. Now, why do I do a scan rate of 10 millivolts per second? Because the scan rate is slow enough that we can get more ideal behavior in our oxidation reduction system here, and I get a more kind of classical CV. I only did one repeat of it, one scan, and I set my current range to 10 micrograms. So there's nothing wrong here, but there is something wrong for me because of the philosophy at ZP. And the ZP does products, but the products have a philosophy behind them. We want to get people to market, and there's something wrong with this assay, and it's actually the estimated runtime is 163 seconds. That doesn't matter when you're teaching in a lab, but I just want to kind of get that philosophy across that, 163 seconds is almost 3 minutes. Time is money. So if you're making an assay for a nurse, or an athlete or anyone, nobody wants to wait almost 3 minutes for the result. So in fact, if you're going to start teaching cyclic voltammetry, make up the solution, 5 millimolar ferricyanide in 1 molar potassium chloride, these settings on that hypervalue carbon electrode, and you'll get a nice CV, and you can explain the oxidation and the reduction peaks, etc. Fine. And I can expand upon that in future webinars, sort of to make it a bit more interesting. But I'm sort of jokingly here saying, by the way, you're doing it wrong, not when you're teaching, but if you are thinking about development. And what you're doing wrong here is, if I was to make this same, if I wanted to get the result in this kind of work quicker, first of all, I could halve the time by doing linear sweep voltammetry. So rather than going cycling there and back, I could just do linear sweep voltammetry. Super easy to do on the instrument. Let me just try and find linear sweep. That's impedance. Slightly random because I've got so many of these next to each other, these QR codes next to each other. I want to kind of capture the right one. I go on either side of it. So it can be a bit random actually sometimes trying to get that linear sweep voltammogram. So I'll try and capture it in a second. Now, what I was doing, the reason I did that was because in fact I kind of started, I don't want to say breaking the rules, but you could accuse me of actually trying to break the rules here, because in fact I'm sharing the wrong screen with you rather, because what I'm trying to do is I don't want people to develop assays that are how do I put it, 163 seconds. I want people to develop assays that are fast. So it's and I know it's sort of stating the obvious a bit, but what I've done is by doing linear sweep voltammetry, I've already just kind of halved the time to do the experiment, and then I've done something really a little bit well, I won't call it that controversial actually. I've just made it 100 millivolts scan rate, because that immediately kind of decreases my experimental time versus the last time by about a tenth of the time. So this is just if you're thinking of actually doing if you're doing a development, and I still get my my peak out of my in this case, because I started in a negative potential, the ferricyanide became ferrocyanide, then I oxidized it back to ferricyanide. So I get a nice fast assay. So it's just one of my philosophical, one of my sort of mantras is like, do it fast. Let's get this assay fast. You'll probably know, if I'll do a couple of demos this evening, and what you'll notice is those assays are quite fast, because people will put the sample on there. They want the result there and then. And just out of interest, if you sometimes are doing sort of micro drops and you wait a long time, the micro drop can start evaporating and stuff. So there are many reasons to do things fast, and one of them is just the user experience. Now, question number 2 is about, if I was to summarize question number 1, I think a good place to start teaching electrochemistry is the cyclic voltammetry of ferricyanide. I think doing the conditions where it's kind of start at minus 200 millivolts, scan to 600 millivolts, do one cycle, do it at 10 millivolts per second, set the current range to 10 microamps. This will all work. Do it in 5 millimolar ferricyanide with a background of 1 molar potassium chloride. That's perfectly fine. And you'll get some good CVs. Just note that if you're like more of a sort of person who's thinking, right, now I want to make an assay for the real world, break some of those rules. Do a linear sweep voltammetry, do it at 100 millivolts per second, and that will then give you an 11-second assay. Hooray! That's a much nicer user experience. Now, I want to go and talk about actual PCO2. So PCO2 is it's the dissolved carbon dioxide in the blood. Carbon dioxide in the blood actually is in equilibrium. I've really simplified the equations here, because you can have bicarbonate in equilibrium with carbonate, but I've simplified it all down. So at a high level, carbon dioxide dissolves in water to give you carbonate plus protons, and there's an equilibrium like constant associated with this. People want to know the PCO2. I say people, clinicians are quite keen to know what the PCO2 is, but the things that we find easiest to measure at ZP are the carbonate and the pH. And by the way, we do now have a carbonate technology. It's on the website, and we've always had a pH sensor on the website as well. So how can I determine POC2 from carbonate and pH? And the quick answer is they are actually connected through that equation. So it means that you can actually measure the carbonate and you can measure the pH, and from that we can actually measure the, or rather calculate the PCO2 concentration. So sometimes in electrochemistry we can't always measure the analyte directly, but we can measure two other things, and as long as we know the equilibrium constant there, then we can actually calculate the PCO2 value from that. If you've got any questions regarding that, I'm not saying it's complicated. It's, you know, there's a fair amount of arithmetic, but it's not, you know, most of you, I'm sure, in a science and engineering background could do it. But if you've got any questions, reach out to us. Question number 3 is a bit, somebody's asking a question. Details on how the electrodes interface with a potentiostat for electrochemical measurement. So somebody's interested in our biosensors, which is I'm delighted by. So I will address that question by slightly changing the camera here. And what I'm going to do is I will take up this potentiostat, which is in my hands. And in fact, I'll flip this down, take that out. So what I've got in here, and if I flip this down again, there's 3 pins there. So those 3 pins are what's making connection with the connection points on this screen printed electrode. It's not hard to align. I can literally just drop that in like that. That's locked in place. Click, done. So in fact, it is very easy to make electrical connection between the sensor or potentiostat and these kind of cartridge screen printed electrodes that we have. That's a real innovation, I would say. People are interested here about electrode specifications on the materials that we use. I mean, the materials that we use at ZP are primarily carbon. I think carbon in terms of probably graphite, gold and platinum. We enhance selectivity and sensitivity. One strategy on selectivity, you could also put /specificities to include enzymes. I'll talk about lactate sensing tonight. So unfortunately, there are thousands of ways of making biosensors. So it's too much of a generic question to really answer, but we can, you know, we make them out of gold, platinum, and graphite generally. How do we enhance sensitivity? In fact, you'll see some papers tonight, you know, on how we enhance sensitivity. I will talk about reproducibility. It's really important. It's it's something that ZP, one of the few companies that does a really good job on, is reproducibility. And then customization. Just out of interest, it's a bad idea if you're doing a program, don't go to customization on screen printed electrodes early on. What people are not telling you is that when you make a custom part, you're manufacturing in low volume, and low volume will mean a high price in order to get high quality. In fact, what we'll end up doing is you'll talk to several vendors and you'll get a low price, but what they won't tell you is actually you'll get a low quality. So be very careful on customization too early on in the program. But we have electrodes in different geometries, but the geometries we recommend at any one time really depend on actually what you want to achieve. And just out of interest, when we are when we are functionalizing, we don't splash the functional material over our counter and our reference. We often make sure that we get the functional material on the working alone. At ZP, if you watch many of our demos, you'll see that we actually, in fact, I'm going to do a couple of demos this evening, so watch those demos, because what you'll notice is that I don't do any I don't do any calibration. And the reason I make this comment is because we don't do calibration, because in fact we make a very good reproducible screen printed electrode. That means that we don't need calibration, which makes for a simpler assay, which makes for a lower cost assay. So at ZP, we do a lot of testing. Rather amusingly, actually, we're doing the testing here in ferricyanide. And we test a lot of our electrodes to make sure that they actually are reproducible. And they are really reproducible. In fact, we had a question a couple of weeks ago, or last week, who was doing work on a caffeine sensor. And their complaint was, oh, well, actually, you know, they're not reproducible. But I genuinely was able to actually bring up, we just happened to have some caffeine data ourselves. And we had, we were just doing it in duplicates. But they were really reproducible. So if you're having problems with ZP screen printed electrodes and their reproducibility, reach out to us, because you'll find as quick as a flash I can demonstrate to you that they actually are reproducible. What I can't always control is other people in their labs. That is something that I'm just not able to always control. But we do, some people criticize and say, what, you're saying that your relative standard deviation is only 5 or 6%? Yes, I am saying that, and that's the stuff that we sell on the web stores. But in order to kind of, have you overall, you need your RSDs, your relative standard deviations, and your diagnostics to be better than 20%. And, we obviously are achieving that. And we consistently do this. And why is that? In fact, I'll do a couple of demos this evening. If my screen printed electrodes are not reproducible, the first people who are going to struggle with this is ZP, because we're the only company that's actually using our screen printed electrodes in our own products. And so each one of these colors here represents different concentrations, all done in triplicate. And you can see how tight our data is. And it has to be like this because we use them in real world products. They're used in the food industry, for example, for testing chilies and ginger, and we'll go into caffeine soon as well. Somebody here is asking us about fabricating lactate sensors. So if you're functionalizing the working electrode, only functionalize on the working electrode. I've got a little diagram to show you that on the next slide. They were wondering why we were insistent on people testing with lactic acid. There's actually two forms of lactic acid, L-lactic and D-lactic. At ZP, we've worked with both isomers. L-lactic is generally what people are referring to when they're thinking about human health and measuring things in sweat and saliva. D-lactic is more associated with microbial and maybe bacterial infections. So with lactic, we were getting a bit of a problem. So lactic acids, sometimes they're in the L form, sometimes they're in what's called the racemic form. It contains D and L. But we were getting a bit confused at some point because people were testing our sensors saying they weren't working, and then we were realizing they were actually testing with D-lactic acid. So it's really the D-lactic that I'm most worried that people are actually ending up testing our sensors with. When you're functionalizing, don't splash the material like this. Get that functional material on that working electrode. So not this, but please do it this way. Why am I saying that? Because there's no point in putting the enzyme on the counter electrode. It's not where it's meant to be. And it can lead to sort of weird phenomena where you've got a reaction taking place on the counter electrode, but that reaction, if it's in terms of a lactic oxidase, it's producing hydroperoxide, which then diffuses over to the working electrode. It's all a bit of a mixed situation. I'd rather have the enzyme where it's meant to be rather than just haphazardly put everywhere. And lactic acid is a good example, actually. It's super expensive enzyme anyway, so you wouldn't want to be wasting material. Just out of interest, this is a side note, but I got this data in this week. Lactic acid sensors are really hard to make, or lactate acid sensors are pretty hard to make. And we just made, so look at this one. This is being tested at different concentrations, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. You can just start to see we're having a Michaelis-Menten limiting current just near the top here. The enzyme's becoming limited. If that term Michaelis-Menten's not super familiar to you, just Google it or put it into on our maybe I'll put a link. No, I'll probably forget to do it, but there's a video on our webpage I put up in November 2024 that you should be able to find on Michaelis-Menten. And I just put this as a sidebar note that we've actually been making these sensors and they work really well. And that's a little peek preview of a wearable potentiostat that's also coming out in probably Q1 2025. If you're going to make a biosensor, and let's say you're going to make an oxidase-based biosensor, get hold of a ZP Platinum sensor, and the first experiment I would do is just sense of what that kind of baseline signal will do. Then, to teach yourself, do a cyclovoltammogram on a solution like 0.1 millimolar hydrogen peroxide, again in PBS, and just look at that difference. Just get a sense of, okay, so that's what the blank potassium sensor looks like. Now I test with a bit of hydrogen peroxide. Okay, now I see the difference. And you can start, because the reason I bring that is, see, with a lactate sensor, you may end up with a platinum sensor, a platinum electrode rather, on top of which you put an oxidase enzyme, on which you may end up putting a barrier layer on, and I suspect you will end up putting a barrier layer on it. But in order to troubleshoot and to learn, start off with simple. Start off with a bare electrode, just run it in PBS. then add in a low concentration hydroperoxide, do a CV, and just see that difference. Because the first thing that will happen when you start building that lactate sensor is lactate will come in, it'll react with the enzyme, you'll get peroxide generated, and you'll be able to then look at this let's say just a pure peroxide signal and say okay, is this making sense? But build up the complexity by sort of building up these first two steps. Just run a CV of 0 millimolar PBS and then a CV of 0.1 millimolar hydrogen peroxide. I hope that will help clarify things a little bit. Just out of interest, this particular client's getting this strange peak here. I must admit, I'm not entirely sure what it is. Is the honest thing. But I'm always curious, so send me data and I'll try to figure it out. Just out of interest, if you're testing, and people who would using this form factor will be testing, and in fact I'll be doing a test in a minute, so hang on and you'll be able to watch something like that anyway. But when you're testing by putting drops on these kinds of sensor, and in fact I'll get a pipette tip while I go along, you're really going to be often working what we call a non-steady state situation. So I'm going to bring that up just to kind of explain what I mean by that now. Alright, so you put that drop on there, and then you turn the kind of voltage on, especially if you're doing amperometry, which is one of the modes that is this potentiostat can definitely do amperometry. I'll just scan that. The wrong one there. Yeah. So now I'm in amperometric mode. Anyway, so this potentiostat can definitely do amperometry. So it's a super elegant little device. You're in a non-steady state situation, so you've got this finite drop on top of this electrode, and you turn on the voltage in amperometry, and you start actually depleting the material next to the electrode. So you don't end up with a steady state current, you end up with a current that's actually falling. Now the current falling is actually falling with a square root of time. The reason it's the square root of time is it's actually following fixed laws of diffusion. So it's a non-steady state system. There's no mass transport. We're not pumping, we're not flowing, we're not stirring. So your signal will fall almost in relation to fixed laws of diffusion. Now electrochemists kind of call it the Cottrell response, and the Cottrell response is really just kind of saying current is proportional to the concentration near the electrode, but this is falling actually as a square root of time. So the current is actually would look like this, and then what I would hope is like at 0 millimolar, maybe lactate as an example, you would have a signal that looks like this. And then if you did the same test, but now at 5 millimolar, you'd have the same kind of non-steady state signal, but it would be higher because now you have the peroxide actually being generated. Now, if you build a lactate sensor, for example, with a barrier layer on it, some of what I just said just stops, actually, not stops, but you actually may have a signal that looks like this, because the barrier layer is slowing up the overall diffusion through the system. And now you're actually just becoming proportional to the rate of diffusion through the barrier layer. You don't build up this depletion layer because, in fact, there's plenty of material in the bulk, but it's the time taken to diffuse across the barrier layer which actually ends up limiting your current. And so you are actually in a steady state situation there. So I had to kind of throw that in because I'm seeing some data coming from one of our clients which looks like it's non-steady state. And then one day they'll end up putting a barrier layer on their sensor, and then they'll be like, oh, now I've got a steady state. What's going on here? It's the barrier layer is now becoming the rate limiting or the diffusion limiting part of their signal. And at that point, they'll actually be steady state. Just out of interest, if you're doing doing amperometry, you often get a charging current. You've got this electrode sitting in the ions. We apply a voltage. The ions rearrange, and you actually get a charge. Now, pure electrochemists think that the current in the first second is just pure charging current and is not useful to them. But actually, we know that within that first second, you get this non-specific charging current. But actually, if you've got a reaction going on, there's also some part of that charging current also has some concentration information tied up in it as well. So don't think charging current is completely useless. I think that was definitely a view that I was given 24 years ago when I first started in industry. But 24 years later, it was like, I think a lot of assumptions in lots of sciences are actually assumptions until somebody actually proves them otherwise wrong, or it's just people realize it's dogma. I would almost suggest it's like dogma. Actually, there is some useful signals in these charging currents, and we use them at ZP. Question number 5. This is a really good one. Something I'm quite passionate about. I was asked, how one would translate a paper such as this. What's the fastest, most efficient way of translating a paper such as this into a commercial product? Now, I'm super biased, but I'm going to do a demonstration in a minute. And in fact, I'm going to move from my amperometric mode or my amperometry mode now. I'm just going to go slightly into ginger mode, which is, ginger mode here. So now I'm in ginger mode. I'm going to do a demonstration in a minute. But I'm going to use a demonstration because I want to show in this particular demonstration, this is not a super nice sample. I mean, admittedly that camera's a bit small. This is not super transparent. It's actually a bit of a sort of a milky kind of like suspension here that I've got. It's actually fresh squeezed ginger. But hold with me and let me get back to what I'm meant to be talking about. So, good paper, good application, interesting target. Is it translatable rapidly into a real product? The quick answer is absolutely it is. So tetracyclines are antibiotics. They're used in the dairy industry, probably used extensively, I imagine, in agriculture. But they are used in the dairy industry. People do not want these residues of this antibiotic in the milk. It can cause downstream health problems. The authors here, this is coming from the University of Strathclyde, have a very elegant way of making a complex between, and it's great because iron 3 is a very redox active molecule. It's already in one of its highest oxidation states. Iron generally has +2 and +3 oxidation state. This is already in its +3 oxidation state, which will really help with things like shelf life of this particular sensor system. The reason I said that a bit like that is because there is an example in nature where iron is actually in its +4 oxidation state, and that's actually in hemoglobin. But it's very rare. I think I've only ever seen it in hemoglobin. But anyway, they have a way of making a complex between the tetracycline and iron. They actually interrogate it at a low pH, which is really cool because, in fact, that is definitely a strategy that at ZP we use quite a lot of. So, in fact, when I do the test tonight, we will also be testing at a low pH. They were using differential pulse voltammetry they use a very sensitized gold electrode. I mean, the gold they use is sputtered, and it's also got electroposited gold on it as well. This is a personal opinion, I really quite like carbon electrodes. Now, why do I say no? I understand the sensitivity of their, and there'll be an IP position here as well. But electrodes like this, these are really low cost to cheap, low cost to produce. We've got them in a very elegant form factor. The way it will actually clip into the potentiostat. We can also do them in gold as well. It's just the one thing about gold is it's 24,000 times more expensive than carbon. And gold prices fluctuate. I mean, in recessions and times like this is when people rush to gold. So suddenly gold is spiking in price at the moment. It's very hard to sometimes have a product in a very cost sensitive market like the dairy market where margins are quite low, and have a product that's kind of dependent on essentially a luxury material. So I do like carbon, and I can quite clearly see that this tetracycline antibiotic ferric complex will also be active on carbon. I can understand their concerns about sensitivity, but I would always try to sort of work on the carbon rather than gold. But that said, they want to do differential pulse voltammetry. At ZP, we like EIS, we like differential pulse, we like square wave voltammetry. I've got a slight preference towards square wave voltammetry. It's just I don't want to say a bias, there's an unconscious bias of anything. I just want to scan the, that's testosterone, sorry. I want to scan, So I put this now into square wave voltammetry. So now I can in fact do square wave voltammetry on this device, in fact using this electrode. So I got a very strong suspicion that this electrode, this device, this square wave voltammetry will run that assay absolutely no problems. I know they're using differential pulse, but square wave is probably pretty equivalent. I do want to do a demonstration in a minute, and even though I'm going to do a demonstration on ginger, I do want you to think of the word milk every time I do that demonstration. So this paper has some relatively simple bioelectrochemistry, or I should just say electrochemistry, and they achieve a good limit of detection. I've actually talked about ferrocyanide quite a bit tonight. So this Fe2 plus Fe3 plus is, and I only use these diagrams from their paper by the authors from the University of Strathclyde. So I just want to make sure that everyone understands the ownership on that. But I quite like this elegance that they form this complex. And, when you look at these tetracyclines, I mean, look how there's a lot of heteroatoms in here. There's a lot of aromaticity. So you can just see the intrinsic kind of, there's a lot of electrochemistry actually associated just in these molecules in their own right, let's say. But I can see that they can have these peaks. I like these peaks as well because these peaks are actually reduction peaks. I think it's actually sometimes quite, in fact, I will do a demonstration in a bit where we use a reduction peak actually in our assays as well. Reduction peaks are quite good peaks to assess. And I say here in a demo, but in this demo, I'll talk about the sample preparation, I'll talk about the measurement, and then I'll do a result as well. So I quite like, this is something that I did earlier on. Now I know this paper is about milk, but I just want to kind of talk about, samples don't have to be clean and elegant in order for electrochemistry to work. So this is literally something I did earlier on. This is, in fact, here it is. So tetracycline in milk. I know this is a ginger root, but we're really talking about complex non-standard samples. In this one I had to kind of prepare it by grating it. I had to press it through a garlic press to get the kind of juice out of it, which I did. And then I did a 1 in 10 dilution of that to actually get this kind of slightly cloudy sample, which I have here now. So what I want to do is I just want to do a quick demonstration or test on this. So the Sensi-All potentiostat is a really unusual potentiostat. I just want to check something here. I'm just going to put some names in so I can find this data in a bit. Demo Strath, I'll put in. Oops. Right. Okay. I just want to do a quick demo because this device is absolutely set up that people can create their own QR codes. And so even though I'm about to test ginger, people, if they're developing something like a test in milk for tetracyclines, they can absolutely create their own QR codes, and actually everything I'm about to do can just become essentially their assay. So let me do a demonstration to kind of show how easy this system is. There are some nice features about this. I might take a fresh sensor because I can't quite remember the history on that particular sensor. So let me take a fresh sensor. No alignment, just click it in like that. Super done, super easy. Another, super benefit of electrochemistry is that we never need much sample. And also this sample is not transparent like an optical system would require. I'm going to go continue. This sample is what's called a 1 in 10 dilution. I'll do a start measurement, and I can see the data coming in real time. But this is a really elegant system because I'm not expecting I want to say farmer. I'm trying to think of a dairyman, let's say, to be interpreting my electrochemical data because that's my electrochemical data. But I just want to show you what's popped up on the phone here. This is the power of this. I have just done cyclovoltammetry in this particular case, but I could have done square wave voltammetry, etc., EIS. But it's come back with a result. I'm going to describe that workflow. In fact, I might even describe that workflow with the next slides. But I'm also going to share something with you online as well. So what just happened was I took the sensor, I put it into the potentiostat, and I put the sample on there. I told the potentiostat what to do by using a QR code. You, if you use this platform, can create your own QR codes, which means then that the QR code will tell the app what it should be doing. The app will tell the potentiostat what to do by Bluetooth. The potentiostat will run. It will grab the raw data And it was so fast, but actually the raw data actually went to the cloud, and we actually processed the data in a cloud system called Djuli, where we found the peak height, and we processed it, and we returned back the information in terms of concentration, because dairy men, or dairy people I should say, do not want my my square wave voltammetry or my differential voltammetry or my square wave voltammetry or my they don't want it. But what's nice is we have a feature, and I'm just going to quickly navigate to it. The data actually went to the cloud, and in fact, if I just do a quick refresh here, which I'm doing, it says Strath here, so that's what I put into the phone, and I can see the cycle voltammetry. I can see these very distinctive peaks, which tell me, that I was, the molecule I was interested in. And it's a bit like the paper, actually, because they had two distinct peaks in their paper as well. And we've also analyzed a reduction peak as well. But what we did is see, if you own this potentiostat, you can program it every time to do what I'm about to show you. So I'll just hide myself for a second so you can actually see it. It's got a data pipe built up here, where in fact we were able to take the second scan, we were able to tell it to go and find a peak height, tell it where to find that peak height, tell it to what equation to apply it to, tell it to show the data. So in fact we were able to, you're able to set a template, which means that every time your assay runs, it goes through this data pipe, finds the peak, finds the peak height, turns peak height into concentration, and sends that back to the phone. So in fact, we can, using this kind of technology, you can develop assays and get things on the market and into the hands of real dairy people, let's say, very, very quickly. I think it's a real game changer in terms of, we're really trying to reduce the barriers between ideas and startups being actually to demonstrate their technology, let's say, in the real world. So that's just something we're really passionate about at ZP. It's the whole sort of raison d'etre of Zimmer and Peacock. So just out of interest, if people need to use a particular electrode, we do have design rules up on the website, so people can just use our design rules and design their own electrodes to fit onto the potentiostat. We also have gold electrodes as well. I know, I do understand, the desire for gold. It is an expensive material, so if but it is expensive. The other thing about gold electrodes as well is I sometimes got a concern that gold is quite good at tarnishing. So I sometimes worry about the shelf life. Carbon is actually more inert than gold. I know it's a bit of an opinion, and I know it can change on the circumstances, but gold can tarnish. Carbon doesn't have such a tarnishing mechanism, and we do have a whole range of cartridges to go with this potentiostat. So I hope that is interesting. Now I'm going to slightly change gears now and talk about dopamine. Dopamine is an electrochemically active molecule. Again, somebody showed me this paper and said, how would I translate this paper into a product? And this paper sort of has a sort of, a kind of format that we really can translate into a product. In this paper, in fact, what they discuss is, this is how we make these quantum materials. So there's a lot of effort in those quantum materials. But then at the end of it, they actually just kind of drop cast them onto, I think it's a glassy carbon disc electrode. Now, this paper is a good one for us because at ZP, we're super passionate about, which is that demonstration that I just did. So if you're, I'm going to do another demonstration in a minute, but this platform, this potentiostat, this app, will be able to translate this paper into a real world product very quickly. Now in this I recognize the potentiostat they're using, the Xenium Pro. So these are quite, large instruments, and are not good instruments for translating the assay out of the lab and into the real world. And the software is also, very electrochemistry kind of centric. But in the end, when I read the paper, they're either using, I think it looks like cyclic voltammetry, but I think I did see, they're using cyclic voltammetry and linear sweep voltammetry. Now, what they're showing quite clearly is that going from a glassy carbon electrode to this sort of nano nano, well, sort of dot-based, nano-dot-based functionalized material, they get a lot more activity. So clearly they have made a very active material. But rather than therefore drop casting onto a glassy carbon electrode, I'd obviously much prefer them to use the 501 carbon electrode, because now they're starting to make a product. So they could effectively do what I was doing earlier on and take some of our screen printed electrodes, functionalize it with their material, put that material into the potentiostat, and almost run their experiment as per normal. Except they are, with this potentiostat, able to create QR codes, so they in fact they can run a dopamine assay as opposed to a just a normal electrochemical assay. Now, what I mean by that is I'll do a demonstration in a minute, but if I was to translate this research into real products, let's say, I would definitely use the Sensi All potentiostat or Sensi All platform. I would definitely be using these screen printed electrodes. Now what I'll do is I'll do a quick demonstration now, but I'm going to do a slightly different demonstration to earlier on. So what I'm going to do is I've got a new electrode in there, a new sensor in there rather. In fact, I want to put what I call a chili sensor actually into there. So let me get one of those and put that in there like that. I'm just going to scan this. There we are. I've got in chili mode now. Right, so let's talk about, even though I'm going to be testing dopamine, let's talk about chili. The nice thing as well is I think they were trying to test dopamine in urine. So the nice thing about electrochemistry, this is a sample I'm going to test. But again, it's not the world's cleanest sample, but that is the benefit of electrochemistry. I might go grab a slightly cleaner pipette though, pipette tip. So I'll grab the pipette tip, I'll put 50 microliters onto the sensor, which I do now. I'm just going to give this a name. I'm going to call it dope. If I can remember how to delete that is. I'm just going to try and name this now. Yeah, sorry, right. So I'll call it, I'm going to call this dopamine. Dopamine. Yep, so I've named that. Done. Samples on there anyway, so I will just go continue, start, and off we go. So again, what's elegant about this system is I'm doing a different assay now, but I'm doing a cyclovoltammetry in fact, but it's going to grab the cyclovoltammetry data, it's going to upload that data very quickly to the cloud, process the data, and actually send me back a concentration. In fact, it's already done it. It's done it faster than I can say it, basically. So amazingly, new sample on there, micromolar concentration, job done. But I want to show you what's happened here. Right, so here is my screen, and I'm going to just go up to here. I will go refresh, dopamine. So I can actually see the peak here. And what we've done again is we've actually measured the peak height, turned it into concentration, and sent the concentration right back to the phone. The problem with a lot of scientific papers is that they will do the raw signal and create a calibration curve. But the big difference with this potentiostat system is we're actually able to go into tools, into properties. I'm actually able to put the calibration factors in this cloud system. So every time the data is gathered, it goes through the calibration, turns peak height in this particular case into concentration and sends it back to the phone. And that means that this is not like another, let's say paper that's then trapped, essentially in the literature. If people are doing biosensor development on the Sensi or potentiostat and using our screen printed electrodes, they're actually able to make an impact then. And I think government's going to be much more happy with people who are able to demonstrate an impact. So you take our screen printed electrodes, put a sample on there, use the QR code to drive whatever assay you want to drive. The potentiostat will give the data back to the app. The app will upload it to Djuli. Djuli can then be programmed to convert it into concentration. It'll actually go back to the phone. So question number 1 was about doing lab experiments on Sensi All. Question number 2 was about PCO2, which is partial pressure carbon dioxide in bloods. Question number 3 was generic questions on biosensors, which, you know, I showed you how easy these sensors are to click in and click out of the SensiAll platform. Question number 4 was about making lactate sensors in the lab. Question number 5 was about how to translate scientific papers really into, let's say, products. And question number 6 was about measuring dopamine. I think they were trying to do it in urine, but because they were doing it on a glassy carbon electrode and using fairly large potentiostat and quite scientific software, very hard to actually then give that to a nurse, etc. But this SensiAll potentiostat will really do that for them. Now, if you've got any questions about Zimmer and Peacock, wearable biosensors, or point of care, point of need diagnostics, don't hesitate to reach out to us. Okay, thanks very much.